Hello Cosmic Explorers, I'm Dr. Maya, and today we're venturing to the edge of our solar system. In September 2025, NASA will launch IMAP, the Interstellar Mapping and Acceleration Probe. IMAP's mission: uncover how particles are accelerated to near light speeds and map the invisible boundary where our solar wind meets the interstellar medium. This is our chance to understand the shield that protects Earth and the secrets of our solar neighborhood. Let's dive into the top 10 insights we expect from NASA's IMAP mission. IMAP. What does it stand for? Well, IMAP stands for Interstellar Mapping and Acceleration Probe. It's quite a mouthful, but the name hints at the mission's ambitious goals. Essentially, it's a particle observatory strategically positioned at the very edge of our solar system. This location gives it a unique vantage point. Now, unlike traditional telescopes that are designed to look at distant stars and galaxies, IMAP has a different focus. It's designed to directly sample the solar wind, which is the constant stream of particles emitted by our sun, and also those interstellar particles that make their way into our solar system from the vast expanse of space beyond. By doing so, IMAP will be mapping our sun's protective bubble, a region of space dominated by the sun's magnetic field. This bubble is known as the heliosphere. The heliosphere plays a vital role, shielding us from a significant portion of the harsh cosmic rays that bombard our solar system. These rays are high-energy particles that can be harmful to life and technology. Therefore, its boundary acts as our first line of defense against this cosmic radiation. IMAP is designed to reveal the precise shape and detailed structure of this crucial boundary. Understanding this boundary is crucial as it directly impacts the protection of life and the increasingly sensitive technology we rely on here on Earth. While previous missions, such as the Voyager probes, have provided us with the valuable snapshots of this region, IMAP will go much further, creating a comprehensive and detailed global map of the heliosphere's boundary. By meticulously analyzing the energy, direction, and even the composition of these particles, we'll be able to decode the fundamental physics that are shaping our cosmic neighborhood and influencing the environment around our solar system. Ultimately, this mission is about gaining a deeper understanding of the complex environment that makes life as we know it possible right here on Earth. And for the first time ever, we'll have the opportunity to truly listen in on the ongoing cosmic conversation, the intricate dance of interactions between our sun and the vast expanse of the galaxy beyond. IMAP's ultimate destination is Lagrange Point 1, often referred to as L1. This special location in space offers a unique opportunity for scientific observation. It's a gravitational sweet spot, a place where the gravitational forces of the Earth and the Sun balance each other out. This equilibrium allows a spacecraft to maintain a relatively stable position with minimal energy expenditure. L1 is located approximately 1.5 million kilometers from Earth, positioning it directly between us and the Sun. This strategic location provides an unobstructed view of our star and the solar wind it constantly emits. Launching in September 2025, the IMAP mission will embark on its journey to this crucial point in space. IMAP will travel a carefully planned path to L1, a trajectory designed to minimize fuel consumption and maximize efficiency. This route will take several months to complete. Once there, it can continuously monitor the solar wind before it reaches Earth, providing valuable data about its composition and behavior. At L1, IMAP will act as an early warning system, giving us advance notice of incoming solar events. This is crucial for mitigating the potential impacts of solar storms and other forms of disruptive space weather on our technology and infrastructure. More importantly, it will collect neutral atoms, those elusive particles that hold vital clues. These are messengers from the edge of the solar system, unaffected by magnetic fields, carrying pristine information about the interstellar environment. Once in its halo orbit around L1, a carefully chosen path that provides optimal viewing conditions, IMAP will rotate and scan the entire sky, methodically gathering data from all directions. This will allow it to build a comprehensive map of the neutral atoms streaming into our solar system over at least 2 years. This isn't a quick snapshot. It's a long-term commitment to unraveling the mysteries of our heliosphere. It's a patient, detailed portrait of our solar system's invisible boundary, the heliosphere, and its interaction with the interstellar medium. The data will reveal details we've only guessed at until now, offering unprecedented insights into the forces shaping our solar system. IMAP's vantage point at L1 is key to unlocking the secrets of our cosmic shield helping us understand how it protects us from harmful galactic radiation. Until now, we've only glimpsed the heliosphere's edge through narrow windows, Voyager's brief crossings. IMAP will create the first global map of this boundary using energetic neutral atoms, or ENAs. When solar wind collides with interstellar atoms, ENAs are created and travel straight back toward the Sun. IMAP will catch these particles, measuring their direction, energy and composition to reconstruct the shape of the heliosphere. Is it a sphere, a comet-like tail, or something else? IMAP will settle the debate. This map will reveal how the Sun's activity and the interstellar medium shape our protective bubble. Understanding this structure is essential for interpreting cosmic rays and solar particles. IMAP will turn our murky cosmic ocean into a well-charted sea. How does the universe accelerate particles to extreme energies? IMAP will investigate this mystery at the edge of our own heliosphere. The boundary acts as a natural particle accelerator, bouncing particles to higher energies. IMAP's instruments will measure these energetic particles in detail, testing theories of acceleration. This isn't just academic. These particles threaten satellites and astronauts. By understanding their origins, we can better predict and protect against space weather. The physics IMAP uncovers here will apply to supernovae and black holes across the universe. Our heliosphere becomes a laboratory for universal processes. IMAP's findings will connect our Sun to the most powerful events in the cosmos. The solar wind, a constant and dynamic emanation from our Sun, is a supersonic stream of plasma. It's not just a gentle breeze, it's a powerful force, constantly rushing outwards at incredible speeds, carrying with it charged particles and magnetic fields. This solar wind permeates the entire solar system, shaping the environments of all the planets and fundamentally shaping our entire solar system. It influences planetary magnetospheres, atmospheres, and even surfaces. To better understand this phenomenon, IMAP, the Interstellar Mapping and Acceleration Probe, will be stationed at L1, a gravitationally stable point between the Earth and the Sun. From this vantage point, IMAP will provide the most detailed measurements yet, meticulously recording the solar wind speed, temperature, density, and the complex structure of its magnetic fields. These measurements will be crucial for understanding the solar wind's behavior. We'll trace solar wind streams back to their origins on the Sun, pinpointing the active regions and coronal holes from which they emanate. This will allow us to improve our understanding of how solar activity drives space weather near Earth, which can disrupt satellites and communication systems. Furthermore, IMAP will study how the solar wind collides with the interstellar medium, the matter and radiation that exists in the space between star systems. This collision creates distinct boundaries, like the termination shock, where the solar wind abruptly slows down, and the heliopause, the outermost edge of our heliosphere, marking the boundary between our solar system and interstellar space. By measuring both outgoing solar wind particles and incoming energetic neutral atoms, ENAs, which are created in these boundary regions, IMAP will reveal the full picture of this complex cosmic interaction, providing unprecedented insights into the dynamics of our heliosphere. This research is vital for understanding how our heliosphere acts as a protective shield, deflecting harmful radiation and shielding us from dangerous cosmic rays, high-energy particles that can damage DNA and electronic equipment. The strength and structure of this shield directly affects Earth's habitability, influencing our climate and environment. It also has implications for future space exploration, as astronauts and spacecraft will need protection from these energetic particles. Ultimately, IMAP will help us refine our models and improve our ability to predict our cosmic protection, ensuring a safer future for both our planet and our exploration of space. IMAP carries 10 advanced instruments, not cameras, but detectors that analyze atoms and particles. ENA images like IMAP Low, IMAP High, and IMAP Ultra will map the heliosphere's boundary at different energy levels. Instruments such as SWE, SWIX, and the magnetometer will measure the solar wind's properties in real time. High-energy detectors like HIT and CODIS will study accelerated particles, revealing their origins and acceleration mechanisms. GCRS will track galactic electrons, and a dust detector will analyze interstellar grains. Together, these instruments provide a dynamic 3D view of our solar system's interaction with the galaxy. Their combined data will offer the most complete picture of our cosmic environment ever assembled. Just beyond our solar system lies the interstellar medium, a mix of gas and dust, the birthplace of stars and planets. Our solar system moves through this medium, currently passing through the local interstellar cloud. IMAP will directly sample interstellar atoms and dust, giving us a pristine look at our galactic neighborhood. The interstellar magnetic field shapes our heliosphere, and IMAP will measure its strength and direction. By analyzing incoming particles, we'll learn about the temperature, density, and composition of the cloud we travel through. This data is fundamental for understanding our place in the galaxy. IMAP will provide the context for our solar system's journey through the Milky Way. The most thrilling part of IMAP's mission is the potential for surprises. Will the heliosphere have a tail, a croissant shape, or something entirely new? IMAP's maps will reveal the truth. IMAP could detect changes in the interstellar medium, clumps, filaments, or new structures we've never seen. The mysterious Ibex ribbon, a giant arc of ENA emissions, may finally be explained. IMAP might uncover new ways particles are accelerated at the boundary. Science thrives on the unexpected, and IMAP is poised to deliver those "that's funny" moments. Each discovery will push the boundaries of our knowledge. IMAP builds on decades of exploration. Voyager's pioneering journey into interstellar space and Ibex's first global maps. Voyager gave us direct measurements at 2 points. Ibex mapped the boundary from afar, discovering the ribbon, but both had limitations. Voyager's data was local, Ibex's resolution was low. IMAP combines their strengths, high-resolution global maps and direct particle measurements from a stable vantage point. Its instruments are 10 to 100 times more sensitive than Ibex's. IMAP will link changes in the Sun to changes at the boundary in real time. This mission turns sketches into a high-definition portrait of our cosmic home. It's the next leap in understanding our place in the galaxy. IMAP's discoveries will ripple across space science, shaping our understanding of astrospheres around other stars. Astrospheres protect exoplanets from cosmic rays, key for habitability. IMAP's data will help us model distant star systems and assess their potential for life. For human exploration, IMAP will improve space weather forecasts, protecting astronauts venturing beyond Earth's magnetic field. This mission is about cosmic self-awareness, understanding our shield, our home, and our connection to the galaxy. IMAP bridges the gap between our Sun and interstellar space. The knowledge gained will guide humanity's future as a spacefaring species. That's our countdown of the top 10 insights from NASA's IMAP mission. From mapping the solar system's edge to decoding particle mysteries, IMAP is set to transform heliophysics. The data will keep scientists busy for decades, revealing the Sun's interaction with the galaxy. What are you most excited to learn from IMAP? Share your thoughts in the comments. Thanks for watching. Subscribe for more cosmic journeys and keep looking up. If you enjoyed this journey, don't forget to subscribe, like, and comment below. Your support helps us bring more cosmic adventures to you.